Hello, in this video we're going to talk a little bit about isotopes and moles. The main questions we want to answer: why do elements have molar masses with decimal places, and what's in a mole? So first, let's address that first question. Why do elements have molar masses with decimal places? When we look on a periodic table, there's not just round numbers. So to address that, let's look at this mass spectrum of neon. So neon is element number 10 on the periodic table. So that means it has 10 protons, 10 electrons, and it looks like a variable number of neutrons. We could have 10 neutrons, and that would give us an atomic mass of 20, or I could have 11 and get 21, or I could have 12 and get 22. So this is evidence that there are actually those three kinds of neons with three different masses. So we call these isotopes. So how do we tell one kind of isotope from another kind of isotope to know what we're talking about? So here is some notation that the textbook uses, where X is our elemental symbol, so neon. Z is the atomic number, 10. And A is the mass unit, or, for example, 20. So note on a periodic table, it looks different. And in the previous video, we made it look like this, right? Where we had our mass number on the bottom of the element and our atomic number on the top. But our book also uses this notation, so I wanted to show you both. So here are some actual pictures of what we can imagine the nuclei of these different isotopes of neon to look like. So if we have neon 20, we would expect there to be 10 protons, 10 neutrons in the nucleus, and 10 electrons outside the atom. So here's a picture of the nucleus with the balls representing protons and neutrons. And we see that as we grow to larger neutrons, the mass goes up by 1. All elements have isotopes, but some are really common and some are useful. And you may have heard of some of them. So deuterium, often used in heavy water, is a very small percentage of water has deuterium, and even smaller, not even measurable percentage is tritium, where we have 2 neutrons stuck in that nuclei. But you may have also heard of carbon-12 and carbon-13. Carbon-13 is used for radioactive. Its radioactive decay is used for determining the age of things. Carbon-13 dating. Okay. So notice, though, that since these isotopes have the same number of protons and electrons, they're still the same element. And they have essentially the same physical and chemical properties. They just have a slightly different mass. And it wasn't until we had mass spectrometers that were precise enough that we could measure the difference that we would know that those were different. So before we talk about molar mass, I want to talk a little bit about what's a mole. So a mole is technically defined as the number of atoms in exactly 12 grams of carbon-12. And we can measure the mass of one carbon-12 atom, and it is 1.9926 times 10 to the negative 23rd grams. What is the number of atoms in exactly 12 grams of carbon-12? So let's think about how we could solve that. Number of atoms, if we have exactly 12 grams of carbon, and we know that one atom of carbon-12 weighs 1.9926 times 10 to the negative 23rd grams in one atom. If we divide this out, we will get the number of atoms in a mole. or 6.022 times 10 to the 23rd atoms. So you may have heard of this number. Avogadro's number before. So that leads us to molar mass, and tying in with that first question of why those isotopes have decimal places. So thinking about molar mass, let's do an example of molar mass. So to find the molar mass of any substance, we need to find the weighted average of the isotopes. So for example, silver has two isotopes, silver 107 and silver 109. The silver 107 has a mass of 106.91 atomic mass units, or if we're thinking about a collection of atoms, we tend to think about that as grams per mole. And it accounts for a little over half, 51.84% of the natural abundance of silver. The rest is silver 109 that weighs 108.90. So we can think about this as a percent abundance or a fractional abundance. So if we're thinking about our weighted average, and this is true for all weighted averages, and especially true for molar masses. So the silver atomic mass is going to be equal to the mass of each isotope. So let's call this one the mass of silver 107 times its fractional abundance, which I'll call A, 107 in this case, plus the mass of silver 109 times the fractional abundance of silver 109. So let's put in some actual numbers. So we have our mass here for silver 107 is 106.91, and its fractional abundance is 0.5184. And the mass of silver 109 is 108.90, and its fractional abundance is 0.4816. So if we multiply these out, we will get 55.42 plus 52.45, which is equal to 107.87. So let's talk a little bit about units. So when we think about the mass of one atom, we tend to use atomic mass units, or AMUs. But when we're talking about a collection of atoms, and what is the weighted average of that collection of atoms, we use grams per mole. So if we have more than one atom, in this case, even if we had one of each, we would use grams per mole. If we were talking about just the molar mass of one atom, we often use AMU to describe that mass.